Every year, humanity pulls off the same impossible trick. We make ordinary rock flow like water and transform it into the foundation of cities, machines, and entire civilizations. But why does rock, where metal sometimes makes up less than a quarter, hide such colossal power? How does stone travel through hellish temperatures, oxygen explosions, and electric arcs hotter than the surface of the sun to become steel, copper, or aluminum? Behind the scenes of this process, there's a moment almost never talked about, a point of no return where the fate of metal and entire industries is decided. Watch this video to the end, and you'll discover what happens in that split second, and why, without it, the modern world simply wouldn't exist. It all starts with ore, rock that contains the desired metal in the form of chemical compounds with oxygen, sulfur, or other elements. Iron ore, copper ore, aluminum ore. They look like ordinary stones, maybe a bit colorful or heavy, but nothing special at first glance. The problem is that even in rich ore, the useful metal might only be 15 to 30%. The rest is waste rock that has to be separated somehow. Mining ore is already an epic undertaking. Open pit mines reach depths of over 1,500 feet and widths spanning several thousand feet. Massive excavators with buckets the size of a 2-story house tear away rock by the ton in a single scoop. Giant dump trucks with wheels as tall as a 2-story house and payload capacities of 300 to 400 tons haul ore to processing plants day and night. In a year, one large mine extracts tens of millions of tons of rock. The first step in processing is crushing. Massive rocks the size of a car enter crushers that break them down into fist-sized chunks. Then these chunks go into mills, cylindrical drums several yards long, filled with steel balls weighing several pounds each. The mill rotates, the balls drop, and pulverize the ore until it becomes a fine powder. The sound of such a mill, a rumble and clatter you can hear for miles. Now we need to separate the valuable minerals from the waste rock. Different methods are used for this. Flotation is one of the most popular. The crushed ore is mixed with water to form a slurry. Then special chemical reagents are added that make the surface of the metal particles hydrophobic, meaning they repel water. Then air is blown through the slurry, creating bubbles. Metal particles stick to the bubbles and float to the top as foam, while the waste rock settles at the bottom. Magnetic separation works for iron ore. Powerful electromagnets attract the iron mineral particles, and the waste rock just falls away. Gravity separation uses the difference in density. Ore with metal is heavier than waste rock, so on special vibrating tables or in water streams, the heavy particles settle while the lighter ones wash away. After enrichment, you get concentrate, a powder where the useful mineral is now 50 to 70%. But this still isn't pure metal. It's a compound with oxygen or sulfur. You need to remove these impurities and obtain the pure element. Let's take iron as an example, because it's the most common structural metal. Iron ore is mostly iron oxides, iron bonded with oxygen. To get pure iron, you've got to strip that oxygen away. This happens in blast furnaces, massive structures up to 100 feet tall and 50 feet across. A blast furnace runs continuously for years. It's loaded from the top in layers: iron ore, coke, and limestone. Hot air, heated to 2,000 degrees Fahrenheit, gets blasted in from below. The coke burns. The temperature inside the furnace hits 4,000 degrees. At those temperatures, carbon rips the oxygen away from the iron oxide. The iron melts and flows to the bottom of the furnace. The scale of the process is staggering. A single blast furnace consumes 3,000 to 5,000 tons of ore per day, about a ton of coke, and produces 2,000 to 3,000 tons of pig iron. That's iron with high carbon content, around 3 to 4%. The molten pig iron reaches temperatures around 4,000 degrees, a true river of fire flowing from the furnace every few hours. When they open the tap hole, an opening at the bottom of the furnace, the molten metal streams out in a brilliant yellow-white torrent into special ladles or channels. The light is so intense, you have to look through dark goggles. The temperature around it hits several hundred degrees, even from dozens of feet away. The air fills with the smell of hot metal and sulfur. But pig iron isn't steel yet. It has too much carbon in it, it's brittle and won't work for most applications. To make steel, you need to drop the carbon content below 2% and remove impurities like sulfur, phosphorus, and other elements. To do this, they remelt the pig iron in converters or electric arc furnaces. The oxygen converter is a massive pear-shaped vessel, as tall as a 5-story building, that can hold up to 400 tons of molten metal. The converter can be tilted to load pig iron and pour out finished steel. When the vessel is filled with molten metal, a water-cooled lance is lowered into it from above, and pure oxygen is injected under pressure. Oxygen is blown through the molten metal at a rate of hundreds of cubic meters per minute. Carbon burns off, creating an enormous amount of gases and sparks that shoot out of the converter's mouth like a volcanic eruption. The temperature of the molten metal rises from the energy released by burning impurities. The entire process takes about 20 minutes, during which 300 tons of pig iron are transformed into steel. Electric arc furnaces are used to melt down scrap metal. Massive graphite electrodes, up to 2 feet in diameter and several yards long, are lowered into the loaded scrap. An electric arc ignites between the electrodes and the metal, reaching temperatures up to 11,000 degrees Fahrenheit, hotter than the surface of the sun. Power consumption hits megawatts. A single furnace can burn through as much electricity as a small town. The metal melts, boils, violently reacts with added flux agents. Slag, a molten mix of oxides and silicates, floats to the surface of the metal and captures impurities. It's regularly tapped off separately. When the metal composition hits the target specs, the melt is poured into a ladle holding dozens to hundreds of tons. This process runs simultaneously at dozens of plants around the world, non-stop, 24 hours a day, 365 days a year. Every year, humanity produces around 2 billion tons of steel. That's roughly 550 pounds for every single person on the planet, including infants. 2,000 million tons. Try to wrap your head around that number. Non-ferrous metals are extracted similarly, but with nuances. Copper often occurs as sulfides, compounds with sulfur. First, the ore concentrate is roasted in furnaces at temperatures around 2,700 degrees Fahrenheit to oxidize the sulfur. Then it's melted at nearly 5,400 degrees, producing matte, an alloy of copper and iron sulfides. The matte is blown with oxygen in a converter, removing iron and residual sulfur, yielding blister copper at about 98% purity. But electronics and wiring need copper at 99.99% purity or higher. This is achieved through electrolytic refining. Blister copper plates get dunked into baths of copper sulfate solution, and an electric current runs through them. Copper dissolves from the anode and settles on the cathode as absolutely pure metal. Impurities either sink to the bottom of the bath or stay in the solution. The process is slow, but it produces the purest copper. Aluminum, that's a whole different story. It's the most abundant metal in Earth's crust, around 8%. But it's so tightly bound to oxygen that extracting it chemically is nearly impossible. Aluminum comes from bauxite, an ore containing aluminum hydroxide. First, bauxite gets treated with alkali under high temperature and pressure to produce pure aluminum oxide, alumina. Then this alumina gets melted through electrolysis in baths of molten cryolite at temperatures around 4,000 degrees Fahrenheit. A massive electric current, tens to hundreds of thousands of amps, runs through the molten mixture. Oxygen gets released at the anode and burns off, while pure aluminum settles at the bottom of the bath. Producing 1 ton of aluminum consumes roughly 15,000 kilowatt hours of electricity. That's about what an average apartment uses in a year. Aluminum plants get built near massive hydroelectric dams because you need cheap electricity in enormous quantities. One modern plant produces 1 million tons of aluminum per year and consumes as much electricity as a city of 1 million people. This is an industry that literally converts electricity into metal. Titanium extraction is even more complex. Titanium ore, titanium dioxide, first has to be converted into titanium chloride, then reduced with magnesium or sodium in sealed reactors at temperatures around 2000 degrees. What you get is titanium sponge, a porous material that then gets remelted in vacuum arc furnaces multiple times to remove impurities. That's why titanium costs tens of times more than steel. Picture this. There's an industrial process where almost 80% of the material just vanishes, but what's left becomes exponentially more valuable. How can wood lose nearly all its mass and transform into a global energy resource that countries pay billions of dollars for? Every year, this product makes a journey from living forests to cargo that crosses oceans, fueling everything from backyard barbecues to high-tech industries. But behind the apparent simplicity lies a dangerous stage where one mistake can destroy dozens of tons in minutes. In this video, you'll see how fire is controlled without flames. And by the end, you'll learn a fact about charcoal that'll completely change how you think about its true cost. Every year, the world burns through roughly 73 million tons of charcoal. That's nearly 200,000 tons a day, enough to bury hundreds of stadiums under a thick blanket of carbon. Despite the rise of gas and electricity, the global charcoal market is worth $3 billion annually. It all starts at raw material yards, where millions of tons of freshly cut logs arrive every single day. First stop, automated sawing lines. The wood gets chopped into standardized lengths, then moves on to hydraulic splitters. Massive steel blades, under incredible pressure, crack the logs into smaller pieces with uniform cross-sections. This isn't for looks. If the logs are too big, the outer shell carbonizes completely while the core stays raw. If the pieces are too small, they'll burn up too fast, turning into brittle charcoal that crumbles into powder. Uniformity of size. That's the foundation of quality, laid down before the first spark ever appears. Freshly cut wood contains 40 to 60% moisture by weight. Evaporating that much water directly in the kilns would be wildly inefficient. So the wood heads into sealed drying chambers. Each batch processes roughly 28 tons of wood over 12 hours. Powerful fans and circulation systems push hot air evenly through the stacks, dropping moisture levels to the critical minimum needed for safe transition to the carbonization stage. After drying, the wood gets loaded into giant industrial kilns. One kiln can hold around 55 tons of wood. This is the most critical stage. The kiln entrance is sealed tight with brick and a thick layer of special clay mixed with sand. This creates a low oxygen environment where combustion doesn't happen. Instead, you get pyrolysis, the chemical breakdown of wood through heat. The process runs non-stop for 7 to 10 days. When the internal temperature hits 572 degrees Fahrenheit, thick white smoke starts pouring from the vents. That's the operator's signal that transformation has begun. Operators, or automated systems, precisely control the air supply. There needs to be just enough oxygen to sustain the reaction, but not enough to let the wood burst into open flame. The result of this process? 55 tons of wood becomes just 11 to 13 tons of finished charcoal. Almost 80% of the original mass is lost, but what remains is pure carbon, lighter, more energy dense, and a cleaner burning fuel. When pyrolysis is complete, the charcoal still holds extremely high internal temperatures. Even the slightest contact with oxygen at this stage can trigger spontaneous combustion. To prevent disaster, the charcoal is left to cool in sealed conditions for 10 to 14 days. It's a test of patience. One tiny crack in the seal, and dozens of tons of product turn to ash in minutes. After full cooling, the charcoal goes through mechanical sorting. Large intact chunks 5 inches long are considered premium product. Every year, just one large plant's automated packaging lines process about 22,000 metric tons of this charcoal, which then gets shipped all across Europe. But what about the small fragments and charcoal dust? At a modern facility, nothing goes to waste. All the charcoal scraps get ground into powder and mixed with natural binding agents, like cassava or cornstarch. The resulting mixture is compressed under high pressure into briquettes, cylinders, or perfectly uniform pillows. These briquettes go through final drying at 280 degrees for 2 hours, becoming dense and stable fuel. When you look at the logistics side of a large modern plant, the numbers get even more mind-blowing. In just one sector, premium lump charcoal production, a single automated packaging line can process over 44 million pounds of product annually. That's tens of thousands of tons of finished fuel, requiring an unbroken supply chain of sourcing, packaging, and transportation. This intensity of operation demands perfect synchronization of every stage, from timber harvesting and days-long carbonization to the instant bagging of finished product that ships worldwide. Charcoal, born from living wood and forged in the fire of sealed kilns, is the result of a remarkable marriage between natural abundance and human engineering. It's a process where wood sacrifices its physical mass and moisture to preserve what matters most in its remains: pure, stable energy, locked away in the form of carbon. Every single charcoal block becomes proof of how humans learned to tame the element of fire, transforming forest resources into a compact and incredibly efficient energy carrier that continues to drive global civilization forward, despite changing eras. When we look at the charcoal production map, it becomes clear that the world is sharply divided between giant producers and equally massive consumers. Today, the undisputed leader in global exports is Indonesia. Just imagine, this country supplies nearly 22% of the entire global charcoal market. Its annual revenue from selling this product exceeds $400 million. As for those buying this resource, that's where things get even more interesting. China leads the world as the top importer, accounting for over 11% of global imports. This isn't just about culinary traditions. Charcoal is irreplaceable in high-tech manufacturing. Think pure silicon for semiconductors. Right behind China, Saudi Arabia, Japan, South Korea, and the US. In these countries, demand comes from two places: the restaurant industry and backyard culture, which pumps billions into the economy every year. The total value of global imports in 2024 alone, nearly $2 billion. Technology keeps pushing forward, especially when it comes to efficiency. Modern plants using pyrolysis retorts, those same ovens we talked about, can squeeze every last bit out of the wood. Traditional earth pits, they give you 15 to 20% charcoal from the wood you load in. That's it. But modern systems, they're pushing 30, even 40% yields. That's massive for the environment. Same amount of fuel, millions of acres of forest saved. And here's the thing, agricultural waste is the new game. Coconut shells, corn cobs, making charcoal without cutting down a single tree. These numbers prove something crucial. Charcoal isn't some relic of the past. It's a dynamic market adapting to modern demands. We're talking billion-dollar operations, cutting-edge materials science, and a lifeline for billions of people worldwide. Every ton of charcoal crossing the oceans, it's a piece of a massive energy puzzle. And production efficiency isn't just a nice-to-have anymore. It's the key to keeping our planet in balance. Imagine a metal that looks like a liquid, moves on its own, and for centuries was thought to be the key to immortality. What if this very substance drove scientists insane, killed entire cities, and still hides underground today, waiting for human error? Every year, the world produces and isolates thousands of tons of this stuff. But the real danger isn't in the numbers. It's that mercury never disappears. It migrates, it accumulates, it comes back. From alchemists who breathed in its vapors to tragedies born from normal water and fish, this is the story of a metal humanity called poison way too late. Stick around till the end, and you'll learn why even today, mercury isn't seen as a resource. It's a threat you can't just bury. In ancient civilizations, people knew about mercury long before they understood how dangerous it was. They found it in nature as cinnabar, a bright red mineral that released mercury when heated. Chinese alchemists thought it was an ingredient for immortality. Egyptians used it in rituals. Romans put it in mirrors and cosmetics. Spoiler, none of this ended well. But back then, nobody was reading safety labels. In medieval times, mercury became the star of alchemy. It symbolized change and transformation because it could be both metal and liquid at the same time. Alchemists believed it was the key to making gold. They breathed its vapors, touched it with bare hands, mixed it with other substances, and genuinely wondered why their hands were shaking, their memory was failing, and weird psychological symptoms were kicking in. That's how the mad scientist trope was born. No memes required, just real consequences. The modern era brought mercury an even bigger upgrade. It was used in thermometers, barometers, manometers, fluorescent lamps, batteries, switches, and even medicine. Yep, doctors once prescribed mercury as medication, for infections, even for bad moods. The biggest fail? Treating syphilis with mercury ointments. The disease might not go away, but poisoning was guaranteed. Who remembers mercury thermometers? Drop a comment if you've got one. It was in the 20th century that humanity started to collectively realize mercury wasn't just weird, it was genuinely dangerous. It's toxic in any form, but especially sneaky because it evaporates easily and builds up in your body. Nervous system damage, coordination problems, memory loss, vision issues. This isn't some thriller script, it's what chronic mercury exposure actually does. The phrase "mad as a hatter" didn't come out of nowhere. Hat makers used mercury compounds, and craftsmen literally lost their minds. Then there's the dark chapter of ecology. Mercury doesn't disappear, it migrates. When it hits water, it transforms into methylmercury and enters the food chain. Fish eaten by humans, and suddenly the toxins inside you. The tragedy of the Japanese city of Minamata became the symbol of this problem. Mass poisoning affecting thousands of people proved that a little mercury is a myth. In the mid-20th century, in the Japanese coastal city of Minamata, a chemical plant spent years dumping wastewater loaded with mercury compounds into the bay. The water looked normal. Fish were biting. Life went on, until people started getting mysteriously sick. First came the seizures, tremors, loss of coordination, speech problems. Then, paralysis, blindness, death. Mercury hit children especially hard. Infants were born with severe nervous system damage, even though their mothers often showed no obvious symptoms. The culprit was methylmercury, accumulating in fish and shellfish, the foundation of the local diet. The toxin didn't disappear or dilute. It intensified at every level of the food chain. For decades, the company and authorities denied responsibility, while victims fought not just disease, but indifference. Minamata showed the world a simple, brutal truth. Even minimal doses of mercury can have catastrophic consequences when they become part of the environment. It was the end of the illusion of safe mercury. Mercury deposits exist today, but attitudes toward them are radically different from centuries past. The primary natural source of mercury remains cinnabar, a bright red mineral, mercury sulfide, which forms in hydrothermal deposits, often near volcanic zones, and fractures in the Earth's crust. It's from cinnabar that metallic mercury was historically obtained through roasting, and this process has remained virtually unchanged technologically. What changed were the scale and the regulations. The largest known mercury deposits in the 20th century were developed in Spain, Italy, China, Kyrgyzstan, Mexico, and Algeria. Spain's Almaden deposit was once considered the world's largest, and for centuries supplied a significant portion of global production. Today, it's basically mothballed, like most classic mercury mines. The reason's simple: demand tanked, and the environmental and health risks became too obvious to ignore. China remains the main mercury producer now, but even there, extraction volumes are way lower than in the past. Many countries aren't opening new deposits. They're working with existing stockpiles or secondary mercury recovered from industrial waste recycling and dismantling old equipment. The world has essentially shifted from active mining to a mode of control and reduction. Modern mercury deposits are increasingly viewed not as a future resource, but as a problem that needs to be safely isolated. Some deposits get shut down, others are reclassified as geological landmarks or monitoring sites. Mercury still sits deep within the planet's core, but its story as a strategic metal is nearly over. Now it's an element humanity handles with extreme caution. Underground mercury ore extraction in China typically starts with a narrow portal carved into rock, the entrance to a mine shaft. It might look like a dark rectangle in stone, reinforced with concrete or metal frames. Inside, a tunnel several yards wide, where small mining vehicles can pass through or conveyor belts can run. The working space is cramped and low. The ceiling's propped up with beams, the walls damp, streaked with reddish or dark brown veins of cinnabar. Lighting: cold fluorescent lamps casting harsh shadows. The air's heavy, so ventilation is critical. Along the tunnels run air ducts, humming and pushing fresh air deep into the mine, while simultaneously pulling out dust and gases. The ore itself is extracted using drill and blast or mechanical methods. First, drilling rigs bore a series of holes into the rock. It looks like rhythmic metal biting into stone. Then, if blasting is used, minimal charges are placed in these holes. The explosions are controlled, small. The goal isn't to destroy everything, but to peel away the rock. After that, the tunnel fills with dust that settles for minutes, while ventilation runs at full blast. Next, mechanization takes over. Front-end loaders rake up the broken rock, or gather it in buckets and dump it into mine cars or onto a belt conveyor. The stone looks uneven, with flecks of red. That's cinnabar, the main target. People try not to touch the ore with bare hands unless they have to. The dust is dangerous, so workers wear respirators, thick coveralls, gloves. How strictly this is enforced depends heavily on the specific operation. If it's a semi-underground or open-pit mine, the picture is different. There you'll see step-like benches cut into the rock where equipment moves around. Excavators strip away layers of ore, trucks haul it up to the surface. But even here they try to avoid huge open spaces, mercury dust and fumes, enemy number one, which is why open pits are less desirable for this kind of metal. All that ore doesn't sit around in the mine for long. It's immediately transported to the surface in sealed containers or on covered conveyors to minimize dust dispersal. At the mine exit, you'll often see washing stations, equipment, and sometimes the workers themselves get hosed down so they don't carry cinnabar particles beyond the production zone. After extraction, the ore is crushed and sent for heat treatment. Cinnabar is heated in specialized furnaces, where the mercury sulfide breaks down and the metal evaporates. This stage is the most dangerous. Mercury vapors are toxic, so modern facilities are equipped with sealing, condensation, and filtration systems. The vapors are cooled, after which the mercury transitions to a liquid state and is collected in sealed containers. Formally, all these processes are supposed to occur in a closed loop with no emissions into the environment. In practice, this is where the biggest questions arise. At large state-run or licensed operations, oversight is stricter. There's air monitoring, waste disposal protocols, and tracking of every kilogram of metal. At smaller or semi-legal operations, the risks are significantly higher, and these have historically been the source of local contamination and poisoning. Picture a machine that doesn't cut metal or melt it. It squeezes it like Play-Doh, but with enough force to crumple a skyscraper. What happens to aluminum when thousands of tons crush it simultaneously, while temperatures climb nearly as hot as a volcano? And why can one mistake at this moment destroy the entire part? Most people have no clue that this is exactly how perfectly straight profiles are born for airplanes, electric cars, and skyscrapers. Hidden here is a technology where seconds determine strength, and cold can be more powerful than fire. Watch this video to the end, and you'll discover the invisible trick that transforms soft metal into something close to armor, something textbooks never tell you about. This is a powerful horizontal hydraulic press with a force measured in thousands of tons. The entire process is divided into several distinct stages where metal transforms from a rough blank into a refined profile. It all starts with an aluminum billet. This is a cylindrical blank that's first heated in a special furnace. Importantly, the metal isn't melted to a liquid state. It needs to stay solid but become pliable, like clay. Typically, aluminum is heated to temperatures between 750 and 900 degrees Fahrenheit. In this state, it no longer puts up fierce resistance, but doesn't flow away either. Next, the heated billet is fed into the press container. From one side, a massive steel ram pushes against it, and on the other side sits a die, an ultra-strong steel plate with an opening shaped like the future profile. When the piston starts pressing on the metal with a force of 5,000 tons, the aluminum has nowhere to go but to ooze through the opening in the die. It looks incredible. From the other side of the steel form, a red-hot metal profile slowly crawls out. It can be hollow like a pipe, or have any other intricate geometry with thin walls and internal partitions. The length of a single profile coming out in one cycle can reach 165 feet. To prevent it from bending or warping under its own weight, a special mechanism catches it and carefully pulls the metal along a long table. When the aluminum profile finally breaks free through the steel die, it looks like a red-hot ribbon of Play-Doh, glowing with a dull heat. At this moment, the metal is in its most vulnerable state. It's soft, pliable, and can easily deform under its own weight. Right here, one of the most spectacular stages of the extrusion line begins, the phase of taming and stabilizing the metal. The moment the profile emerges, it enters a zone of intense cooling. Picture a long tunnel filled with either roaring aircraft-grade fans or a fine water mist system. For aluminum, this is a critical moment that metallurgists call press quenching. Speed is everything here. The metal needs to cool from nearly 2,000 degrees Fahrenheit down to 750 in a matter of seconds. If you do it too slowly, the magnesium and silicon particles inside the alloy will cluster together into large clumps, and the metal will stay soft. But if you hit it with cold instantly, these elements freeze in an evenly distributed state, creating a strong crystalline lattice. You literally see the metal's color shift from reddish-gray to that familiar silvery matte finish we all know. The profile doesn't just exit the press. It's carefully escorted by a special robot puller. It clamps the leading edge of the hot metal snake and drags it along a table stretching up to 160 feet. This keeps the profile from tangling or warping into waves while it's still hot. Once the long strip is cut from the press, it moves to a cooling bed. This massive table of beams lets the profile step sideways, continuing to cool down to room temperature. At this stage, the metal looks finished, but that's an illusion. Because of uneven cooling, the elongated profile often looks like a bent noodle. It might have a slight arc or be twisted like a propeller. This is where the real power play happens. To make the profile perfectly straight, they use a device called a stretcher. Two powerful hydraulic grippers grab the metal strip from both ends. On the operator's command, the grippers start moving in opposite directions. They pull the aluminum with enough force to make it elongate slightly, usually between 1 and 3%. At that moment, something physically remarkable happens. All the bends, twists, and internal stresses disappear. The profile straightens into a perfect line. On top of that, this stretching actually strengthens the metal, making its structure more stable. Now, if you look along the profile, you won't see even a millimeter of deviation. After straightening, the perfectly straight metal giant feeds into the cutting table. Massive diamond-coated circular saw blades go to work here. They spin at high speed, slicing through aluminum clean and burr-free. Most commonly, profiles get cut into logistics-friendly 20-foot chunks. But even after this, the metal hasn't reached its maximum hardness yet. The final touch? The aging oven. Cut profiles get stacked into baskets and sent into an oven where they bake for several hours at around 400 degrees. This completes the formation of the metal's internal armor once and for all. What comes out is the exact same part you see in your window frame or solar panel structure. Lightweight, perfectly straight, and incredibly strong. Extrusion is incredibly efficient when it comes to resource use. With extrusion, the metal utilization rate hits 95%. Nearly all the aluminum that goes into the press becomes a useful product. The scraps left over after cutting the profiles are 100% recycled right there at the plant. Producing aluminum from scrap consumes just 5% of the energy needed to produce primary aluminum from ore. Today, roughly 75% of all aluminum ever produced by humanity is still in use, thanks to endless cycles of recycling and extrusion. Typical presses for window profiles operate at forces ranging from 1,500 tons to 3,000 tons. But for aerospace and defense, there are giants with forces exceeding 15,000 tons. They can extrude entire aircraft wing sections or railway car components. Modern high-speed lines can extrude thin-walled profiles at speeds exceeding 500 feet per minute. That means in just 1 hour, a single press can produce over 4 miles of aluminum profile. Interestingly, a single modern electric vehicle can contain anywhere from 177 pounds to 265 pounds of extruded aluminum, which significantly reduces its weight and increases its range on a single battery charge. Next, the profiles can undergo anodizing. While aluminum naturally resists corrosion pretty well, without special treatment, it quickly dulls and develops unsightly stains. Anodizing doesn't just paint the metal on top, it transforms its surface at the molecular level, creating a protective layer that's second only to diamond in hardness. Unlike regular painting, where a layer of paint sits on metal like skin on an apple, anodizing is a process of growing a protective layer from the metal itself. This happens in giant tanks filled with electrolyte, usually a sulfuric acid solution, where aluminum profiles are submerged. An electrical current runs through the tank. The aluminum profile connects to the positive terminal of the power source, the anode, hence the name of the process. Under the effect of electricity, oxygen molecules from the solution literally crash into the metal surface and bond with it. The result is a transparent, incredibly hard layer of aluminum oxide forming on the surface. This layer grows both into the metal and outward, becoming an integral part of it. You can't chip it off or peel it away because it's an extension of the metal itself. If you look at an anodized surface under a microscope, it resembles a honeycomb. The entire protective layer is riddled with billions of microscopic pores, so tiny they're invisible to the naked eye. These pores are what allow aluminum to take on those luxurious colors. When the profile comes out of the electrolytic bath, it can be dipped into a dye. The color penetrates deep inside these honeycomb structures. Because the dye sits inside a hard crystalline structure, it never fades in the sun and never wears off. That's how you get those gold, bronze, black, or silver profiles you see on modern business centers. What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, only to be reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore ignite like little controlled earthquakes. In this video, you'll discover things you never suspected, And by the end, the main secret will be revealed that will forever change how you think about zinc. Zinc is the fourth most consumed metal in the world, right after iron, aluminum, and copper. That alone tells you just how critical it is for the global economy and industry. Annual worldwide zinc production runs somewhere between 12 and 13 million metric tons. We're talking massive volumes here, which really drives home how irreplaceable this metal is across hundreds of different applications. The main zinc mining regions are China, Australia, and Peru. These three countries together account for a huge chunk of global zinc ore production, making them the key players in the market. For instance, China isn't just the world's largest producer, it's also the biggest consumer of zinc, which reflects its massive industrial growth. Other major producers include India, the United States, Mexico, and Canada. As for reserves, the US Geological Survey estimates that global zinc reserves sit at around 250 million metric tons. Beyond that, there are what we call resource bases, essentially potential deposits that haven't been fully explored yet, or aren't economically viable to mine right now. These are estimated at over 1,800,000,000 tons. These numbers tell us that zinc, unlike some rare metals, will be around for many decades to come, even with consumption on the rise. The biggest user of zinc is the galvanizing industry, which uses it to protect steel from corrosion. This sector accounts for roughly 60% of all zinc produced. This shows just how critical zinc is for construction, automotive manufacturing, infrastructure production, and countless other industries where steel's strength and durability are essential. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a huge spike in resource demand. 15 to 20% of zinc is used to produce alloys like brass and die casting alloys. These alloys are used in making parts for cars, household appliances, toys, plumbing fixtures, and electronics. Another 10 to 15% goes into making zinc oxide and other chemical compounds. Zinc oxide has a ton of uses, from sunscreens and cosmetics to paints, ceramics, the rubber industry, and even animal feed supplements. Its antibacterial and protective properties make it a versatile ingredient. The rest of the zinc goes into battery production, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, since zinc is essential for the human immune system. When it comes to pricing, like most commodities, zinc prices fluctuate based on global supply and demand, economic cycles, and the situation in major producing and consuming countries. However, demand for zinc remains stable or growing, driven by urbanization, infrastructure development, and the worldwide need to protect metals from corrosion. This makes zinc an important indicator of global economic health. Most zinc is extracted from underground mines. These are entire underground cities stretching hundreds of feet and sometimes several miles beneath the Earth's surface. We're not talking about simple holes in the ground. These are networks of tunnels, shafts, ventilation systems, and hoisting structures. It all starts with exploration. Geologists work like detectives, searching for what's called ore bodies, sections of rock where the concentration of zinc is high enough to make mining it profitable. Now, zinc typically shows up as a sulfide ore, like sphalerite, and it almost always comes bundled with lead, silver, and sometimes copper. Once they've located a deposit, the real work begins: building the mine itself. This involves sinking vertical shafts that serve as the main access points for getting to the ore, hauling materials up and down, and moving equipment in and out. They also create horizontal tunnels, what miners call drifts, that lead straight to the ore veins. The actual ore extraction is where things get dynamic and risky. Miners bring in specialized gear, powerful drilling rigs that bore holes into the rock face, called blast holes. These holes get packed with explosives. Then comes the carefully controlled blast that breaks apart massive volumes of rock. Think of it like a controlled earthquake on a smaller scale. Dramatic, but completely under control. The dusty air is quickly removed by powerful ventilation systems, which also bring fresh air deep underground. The blasted ore is then loaded into massive underground haul trucks or onto conveyor belts using heavy-duty loaders. It's like a non-stop underground highway, constantly moving tons of ore to the main hoisting shafts. From there, the ore is lifted to the surface using powerful elevators or specialized conveyor systems that climb hundreds of feet vertically. At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a processing plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore feed into crushers that break them down into smaller pieces with a deafening roar. This crushed ore then goes into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore gets ground down into an extremely fine powder, almost like flour. This is critical to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder gets mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. Particles of zinc mineral latch onto these bubbles and float up to the surface, creating foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can pack up to 60% zinc. Since zinc often hangs out with lead, the plant might run several flotation cycles to separately pull out zinc concentrate from lead concentrate. The zinc concentrate you get, it's still not pure metal. It's got to go through metallurgical processing to turn into actual metallic zinc. And this is where we enter the world of extreme temperatures. If they're using the pyrometallurgical method, the zinc concentrate first gets roasted. The concentrate is heated in special furnaces at around 1,800 degrees Fahrenheit. This burns off the sulfur that's part of the sulfide ore, converting it into zinc oxide. During this process, the sulfur transforms into sulfur dioxide gas, which gets collected and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable byproduct. Next, the zinc oxide gets mixed with coal and heated to even higher temperatures, over 2,200 degrees Fahrenheit, sometimes reaching as high as 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process takes place. The carbon strips away oxygen from the zinc oxide, releasing pure metallic zinc. And here's where that amazing evaporation effect happens. At these temperatures, the metallic zinc transitions into a gaseous state. Basically, it evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is way higher, zinc literally turns into vapor that rises up and gets captured in special condensers. There, the vapor cools down and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or pellets. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? Every year, humanity produces over 360 million tons of plastic. Most of it doesn't disappear. It decomposes over hundreds of years. But what if instead of oil, we could make plastic from sugar? In the very heart of Thailand grows a crop that can change this. Sugarcane isn't just a plant, but a solar biofactory that transforms light into the material of the future. From its sweet juice is born polylactide, a bioplastic that decomposes naturally. How do they create eco-friendly packaging from simple cane that could save the planet? Watch till the end, and you'll discover the secret the industry has been keeping quiet about. Sugarcane is a true biofabricator of solar energy. It belongs to the grass family and is grown mainly in warm, humid regions, such as Thailand, Brazil, or India. In Thailand, particularly in Chiang Mai, cane occupies thousands of hectares and is a key crop for the agricultural economy. Cane isn't grown from seed. It's propagated through cuttings, pieces of stems that have nodes with buds. They're planted in prepared soil, usually in furrows, at a depth of 2 to 4 inches. After a few days, the buds sprout and new shoots begin to form. This plant is very light-loving, so plantations are located in open areas. It needs lots of water, but doesn't like stagnation, so irrigation must be moderate and regular. Over 10 to 14 months, the cane grows to 7 to 14 feet tall. Its stems are thick, juicy, filled with sweet juice. It's in this juice that sucrose is contained, the basis for sugar production. During growth, the cane actively absorbs carbon from the atmosphere, converting it into organic substances. This makes it not only a source of energy, but also a natural absorber of greenhouse gases. Sugarcane is harvested when it reaches maximum sucrose concentration, usually 10 to 14 months after planting. In Thailand, The harvest season falls during the dry period, from December through March, when the plant is no longer growing but accumulating sweet juice. In many regions of Thailand, manual harvesting is still used. It's hard work performed by experienced workers with machetes. Before this, the plantation is often burned to remove leaves and ease access to the stems. Although this simplifies the process, burning harms the environment, so more and more farmers are switching to green cane. Harvest without fire. Large farms use mechanized combines that cut, clean, and chop the cane right in the field. This is faster, more efficient, and more ecological, though it requires investment. Important: cane residues, bagasse, aren't thrown away. They're used as biofuel, fertilizer, or even for making paper. This is an example of circular economy where nothing is wasted. After harvest, the cane must reach processing as quickly as possible. Otherwise, the sucrose level in the stems begins to drop, and that means quality loss. So logistics here is critically important. Trucks are the most common option in Thailand. Special open platforms or beds with high sides allow transporting large volumes of cane. Buggies or tractors with trailers are often used for short distances, from field to loading point. In some regions where there's appropriate infrastructure, cane is transported by rail cars. This is efficient for large volumes and long distances, but less flexible than motor transport. Water transport is a rare but possible option in areas with canals or rivers. It's used mainly for export or movement between regions. Cane is often not chopped in the field, but transported in whole stems. They're laid horizontally, densely, to minimize losses. At the factory, chopping, pressing, and juice extraction already occur. Large agricultural enterprises use automated loading systems that speed up the process and reduce losses. In smaller ones, work is still done manually or with simple mechanisms. When trucks with sugarcane arrive at the factory, the technological process begins that transforms the green plant into an innovative material, polylactide. This is a complex but fascinating journey where agricultural biomass becomes part of the ecological future. Before the cane enters processing, it's checked for sucrose content. Samples are taken from each batch to determine how suitable it is for production. Then the stems are cleaned of leaves and foreign impurities, manually or mechanically. Then our cane needs to be chopped. For this, the stems pass through mechanical crushers. These are large rollers or rotary machines with sharp blades that cut the stems into small fragments. The goal is to maximally open the cellular structure to ease juice extraction. The chopped cane is pressed in special rollers. Under high pressure, sweet juice rich in sucrose flows out. This juice is collected in reservoirs. The juice undergoes filtration to remove impurities, and then is heated for concentration. Next, a process similar to brewing kvass or yogurt is launched. Special bacteria are added that transform sugar into lactic acid. It's like when microbes turn grape juice into wine. Only here it's not alcohol that comes out, but acid. This process is called fermentation. It occurs in large tanks, bioreactors. There, everything is controlled. Temperature, acidity, how many bacteria are there? So they work properly and don't slack off. Lactic acid is the key ingredient for creating bioplastic. It has properties that allow transforming it into a polymer. The lactic acid is purified and subjected to polymerization, a chemical process in which molecules connect into long chains. The result is polylactide, a thermoplastic polymer that looks like granules or threads. These granules or threads are the basis for producing packaging, tableware, textiles, 3D printing filaments, and other products. Polylactide has high transparency, strength, and heat resistance, making it an ideal substitute for traditional plastic. Polylactide granules are poured into special machines, extruders or thermopresses. There, they're heated to the required temperature until they become a viscous mass. The hot mass is passed through forms or dies. For packaging and bags, the extrusion method is used. that is, pulling hot polymer into long ribbons or film. Cups, containers, spoons, and so on are made by filling corresponding forms with polymer under pressure. To create more complex shapes, like coffee lids, heated film is pressed to the form with a press. As soon as the product is formed, it's quickly cooled with water, air, or special cooling plates. This is needed so the material hardens and doesn't deform. Finished products are trimmed, polished if needed, checked for quality, and packed for delivery. Before packing, each product undergoes visual inspection or automatic checking for defects, cracks, deformations, irregularities. In large productions, this is done by robotic systems with cameras and sensors. Defective products are often remelted, since polylactide allows reuse without quality loss. After final cooling, polylactide products, still warm from machine touch, set out on their last journey, to the packing line. Here, everything works smoothly. Mechanical arms carefully stack cups in perfect stacks, 50 in each. Product groups are wrapped in biodegradable film or cardboard boxes. Packaging can also be made of polylactide. That is, the product and its wrapper are made from the same material, which simplifies recycling. Afterward, labels are applied with information: polylactide type, production date, batch, disposal instructions. Finished boxes with products are stacked on pallets, wrapped with stretch film, which is often also bio, and sent to warehouses or to customers. Storage temperature is room temperature, but without excessive humidity, so polylactide doesn't start decomposing prematurely. Green packaging is no longer just fashion, but a demand of the times. Videos about plastic harm get millions of views, and brands are looking for alternatives that don't harm the environment. Polylactide from cane is one of the most promising options. After all, cane grows quickly, and the production process doesn't require crazy resources.